Okay, so this is chapter 5, problem number 22. Talking about a car running into a barrier, and they want you to show using this impulse momentum theorem that this equation holds true. And so what happens is when a car runs into something, the bumper is what cushions the blow, and so the impulse, it allows for the deceleration to happen over a shorter period of time, so the impulse is less. So this delta p, which is impulse, is mass times velocity final minus mass times velocity initial. I just substituted in momentum for these two equations. Now initially looking at this problem, it's a little confusing. What I found though is that there's this equation from kinematics. We have velocity final equals velocity initial plus 2a delta x. And I found that because if you look up here, there's a delta x. This is my thought process, I guess, here. I saw a delta x in that equation, and we have velocities. I got velocities. And so this just seemed to be one where if I have a final and initial velocity and a distance in which the vehicle stops, which is what the bumper allows us more of, and then we got an acceleration. This force has an acceleration in it, so I saw this here too, because F equals ma. So I don't know, I just picked that, right? And then so what I tried to do is I tried to make it look like this equation. So what I did is I subtracted v, like in our book, v initial is 0, and then v final is just v. So I went back to what our book does right here, and so we have, I just subtracted v initial right here, v0 squared, from both sides, and then I divided both sides by 2, and so then I got this equation right here where it's 1/2 v2 minus v, or v minus v0 squared equals a delta x, right? And so I got that, and I just kind of got confused. Well, if you look up here, there's a mass involved here, and there F equals ma, so there's a mass involved there. So what I did is I just tried something, and what I did is I multiplied both sides by mass. Once I multiply both sides by mass, I get this 1/2 mv squared minus v0 squared equals m times a delta x. Now this ma, F equals ma, and I didn't really see that coming, but there it is, F equals ma. So I'm able to take and substitute in for this ma, I was able to substitute in force, right? And then over here we just still have 1/2 mv minus v0 squared, or v squared minus v0 squared equals f times delta x. Now we're getting closer to that. So I have the f delta x, which is up here, and then I have this 1/2 mv squared. So here I have 1/2 m, and then I have the v's, so I'm really, really close. So the next step, if there is a collision, a vehicle, and it's going to hit and the bumper is going to do its job, then the v, which is the final velocity, should go to 0. So that goes to 0, and I get this equation, which is 1/2 m times negative v0 squared equals f times delta x. Now I put this negative here. Some people may wonder about that. Well, here's a little picture. If I have a car with a velocity and it's going to run into this and my bumper is going to do its job, the acceleration is going to be in this direction. This is the positive direction, the direction we're going. The acceleration is going to be the opposite. And so what I did is I thought, all right, so since the acceleration is going to be the opposite direction, that means this a right here is negative. That means this f is negative. And so I get f delta x equals 1/2 mv0 squared. So the force times the distance in which the bumper compresses is equal to 1/2 mass times velocity initial. That's the initial velocity the vehicle brings to the collision, squared. And that is the equation that they wanted us to prove.